I'm Mark Brooker. I'm coming pre-recorded so I can answer your questions live in the chat box during the presentation. Today I'm going to be talking about our paper on Firecracker, which is lightweight virtualization for serverless applications. I'm going to cover what is Firecracker, why we built Firecracker, some of the performance figures that we got when we tested Firecracker, and some of the challenges we see for the future of research into lightweight virtualization and virtualization for serverless applications. Firecracker is an open source VMM, a virtual machine monitor that is purpose-built for creating and managing secure, multi-tenant, container and function-based services. Let's talk a little bit about how that fits into the virtualization stack. There are obviously many ways to architect a virtualization solution. But within the Firecracker world, we built on top of Linux's KVM. This is a feature, the kernel virtual machine is a feature in the Linux kernel that allows us to build virtual machines using a standard API, right? We say to the kernel, start us a virtual machine, and then the kernel handles the heavy lifting of virtualization on the platform, handles all the hardware details, handles page tables, and some of the other tricky low-level details. Firecracker sits next to KVM, running there on top of the host kernel, and provides, firstly, it does setup of KVM. It talks to the kernel and says, set up this VM for me, and does the I/O virtualization. And so it handles block I/O and handles networking and so on. We built Firecracker starting with a branch of CrossVM. Because we were specializing for serverless and specializing for these lightweight cloud workloads, we started off by removing about 50% of the code of CrossVM. So this was taking out a lot of stuff in that code base that we didn't need. Although CrossVM was already quite small, and so what we ended up with at the end of this was something that was about 96% fewer lines than QEMU, 4% of the size of QEMU, which is the standard VMM that folks tend to use in this kind of architecture. Firecracker has a simplified device model, and what that means is there's no BIOS. It boots the Linux kernel directly. There's no PCI, so there are no kind of virtual PCI devices. The kernel talks these protocols of VirtIO net and VirtIO block and so on directly. And so there's a great deal of simplification there, and a great deal of simplification both of the guest kernel and of the VMM. Firecracker supports both Linux and OSV guests. Our deployment in AWS is with Linux guests, and the OSV microkernel also boots really quickly and impressively on Firecracker. We've integrated and worked with the open source community to integrate Firecracker with the container ecosystem. There's Firecracker support in or going into Kata containers. There's a Firecracker integration into Kubernetes called Firecube, and Firecracker integration in Containerd. And what these do in the container ecosystem is allow you to replace the standard Linux container type isolation mechanism with this much stronger isolation mechanism provided by virtualization. Firecracker is available with open source. It's on GitHub. This is the same code that we run in production in AWS under the Apache 2.0 license. And we invite the community to take part, contribute both code and pull requests and so on, and are following a fully open source development model. Firecracker is in production today in AWS Lambda. This is our serverless function service. In production in AWS Lambda, we are handling millions of concurrent workloads on top of Firecracker. So we're running millions of concurrent workloads on the stack already, and that is trillions of requests per month. Sometimes my team jokes that we think we've started more VMs in AWS Lambda in the last 18 months that we've had this in production than everyone else has started in the history of virtualization, such as the scale that we use this at. So why did we build Firecracker? Well, part of that is a story about economics. And so we run Lambda on EC2, the same instances that you can get from EC2 publicly, and on bare metal EC2, because we need the access to bare metal to be able to do virtualization. But these M5 metal instances that we run on are very big. And that's just due to the economics of cloud, right? These things have 48 cores, they have 384 gigabytes of RAM, and are, they're relatively normal servers, but relatively normal servers these days are just big. Whereas the smallest Lambda function is only 128 megabytes. The smallest function that will let you configure is 128 megabytes of RAM, and I can't go and buy a server that is 128 megabytes of RAM, right? Like even embedded sort of Raspberry Pis have more RAM than that these days, and so we need some way of taking these metal instances and cutting them up into many pieces, and there were some properties that we needed to do that, and the most important property is isolation. We want to run many functions, up to thousands, so you can fit about 4,000 of the smallest ones onto one of these big boxes. And it must be safe for these multiple functions to run on the same hardware. And that means safe from a security perspective specifically. We need to be able to run thousands of functions on a single machine with acceptable overheads and acceptable densities. And this is what sent us down the path initially of customizing virtualization for the serverless workload, right? It was overhead and density. We really needed to get the great isolation properties we get out of virtualization, but the overhead and density of container type technology. And we didn't want to be forced into this decision of low overhead we wanted both great security and very low overhead. We also need great performance. Our functions must perform similarly to running natively, both in CPU and in low level things like page table changes and in IO and so on. Customers of AWS don't want to lose performance when they choose serverless. They want a serverless solution that performs, just like their container solutions do, and just like their instances do, and just like their legacy servers do. And so we didn't want any compromises on performance. We needed compatibility. The Lambda product allows customers to bring arbitrary Linux binaries. And that's important because it lets people bring, legacy code bases, bring this code that you've been building up for decades, and trust and know about and understands your data formats and so on, and bring that to the cloud. We didn't want to say, we want you to be able to bring the code that you know and the code that you have without major changes, and even sometimes without recompiling it, and run it here in our serverless compute. We needed soft allocation, right? Like we needed to be able to run these many workloads on a box in a way that didn't commit the worst case amount of memory and worst case amount of CPU to each one. Instead, for economics, what we wanted to be able to do was take the actual amount of CPU and actual amount of memory that each workload was using at each moment and consume that from the machine. So instead of hard allocating 128 megabytes of memory, we can go and get memory on demand. Instead of hard allocating one core, we can schedule on demand and so on. And so Firecracker ticks all of these boxes for us, and virtualization ticks all of these boxes for us. The alternative in the virtualization space of using QEMU with KVM had density and overhead challenges. QEMU is a great piece of software. We have, we've worked with that community for years, but wasn't optimized for this high density and low overhead environment. Linux containers, which are normally the solution or the common solution in this space, had isolation challenges and compatibility challenges. Isolation, we didn't think the security model was strong enough for our customers, and compatibility, we wanted to make sure that all software ran on this platform. Library OS approach is very commonly used too. Big compatibility challenges there. A lot of software is written to assume Linux, assume a particular kernel, assume there's a user land there, and so on. And so these challenges are very, library OSs can be very interesting from an academic perspective, and we're very excited about that community, but they weren't a good fit for Lambda because we wanted people to bring their unmodified software. And similarly with language VM isolation, right? Things like V8 and Java have these features where you can, create isolates within the language VM. We didn't like the security model of those, and we also didn't like the compatibility because we wanted people to be able to bring binaries rather than just, build code in particular languages. We were very happy with Firecracker ticking all of these boxes. Let's talk a little bit about the performance that we got. One important thing in the serverless world is micro VM start time. So we want to boot up. We boot up a lot of these things, as we said, millions of concurrent workloads, and how much time it takes to boot one up is an important, important for our ability to quickly change from one workload to another. So QEMU takes about 200 milliseconds, between 200 and 250 milliseconds to start up in this test, which is serial, one after another. And Firecracker and Cloud HV, which actually shares a lot of Firecracker's DNA, start up in around the 100 millisecond range. The next test, and this was an important one for us again because of how quickly we change workloads inside Lambda, was launching many micro VMs in parallel at the same time. And here's where Firecracker really shows the optimization work that we've done. So in this test, we launched 50 micro VMs all at the same time. They're 50 kind of concurrently starting up in parallel. And you can see that there's quite a long tail on QEMU due to contention in some pieces, whereas Firecracker continues to start up in this kind of 100 millisecond, 120 millisecond range, right up to relatively high percentiles. And this was very important for us and something that was a nice outcome of the optimization work that the team did. Look next at QDEP1 IO latency. So this is kind of serial IO latency, send one, wait for it to be done, send the next one. 4K reads and 4K writes, really great IO latency here. Similarly with 128K read, what you can see there is we're starting to have about a 2x overhead over bare metal. So that's an overhead of about about 400 microseconds at the 428K reads, and that's mostly a bandwidth limitation. We've got an extra memory copy. 128K writes, similarly, some overhead over bare metal, but generally good performance, and performance that is nice, comparable to local SSD, especially for those small reads and writes, and that's important too. As we go to QDEP32, so this is driving 32 parallel requests through the IO layer. You can start, and this is looking at throughput rather than latency. So here, higher is better. And you can see that that Firecracker and Cloud HV, which shares a lot of Firecracker's code in this path, perform relatively poorly today for 4K read and 128K read. And this is because the current code base is not able to handle multiple concurrent IO requests, so it ends up serializing IO requests in the back end. This is something we are working on improving. We know there are ways to improve it. One other interesting here is you can see 4K writes are actually faster, 128K writes are actually faster on Firecracker. And this is actually because of another limitation in our I/O layer, in that we aren't respecting the request to sync to disk. And so those writes look fast because they're going to the page cache of the host, and that allows more reordering and so on. And that's something else that we're adding over time as a set of feature requests. Here are some of the things we learned as we rolled out Firecracker to our Lambda fleet. Operational lessons are one of the things that we sort of really bake into Firecracker, and one of the things that we think brings great value as a contributor to the open source community, as we take these lessons that we learn running AWS and build them into the software that we release. Lesson number one is that compatibility is hard. Relatively tiny changes, like we changed our legacy stack, which was just running on EC2 instances, to our Firecracker-based stack for Lambda. And on the Firecracker side, for security reasons that we discuss in the paper, we disabled hyperthreading. And just disabling hyperthreading revealed two concurrency bugs in Apache Commons HTTP client, and one in our own SDK code. We've upstreamed fixes to both of those, but a very small change like disabling hyperthreading can break code. And this is one of the things we like about virtualization, we like about booting real Linux, is that re-implementing OS components, implementing a library OS, for example, has even more compatibility challenges, or vastly harder compatibility challenges. And running a Linux kernel in the guest with the code that knows how to run on Linux allows us to avoid a lot of compatibility challenges. And then finally, performance compatibility is important too, right? Like, you don't want to have vastly different performance when you move from the cloud to, from an instance or container into the serverless world. Our second important lesson, and this is something we learned operationally, kind of running Lambda and running this fleet on top of Lambda, is that we build our whole fleet on immutable time-limited machines. With a big fleet like our compute fleet, it's attractive to say, well, we're going to maintain that by using these package management tools like RPM and installing new versions of things over time. And what we quickly found was, in that size fleet, small non-determinisms in things like RPM and depackage were causing the software versions in our fleet to just diverge. So what we've moved towards is we have no machine in our fleet over a day old. We stamp them out with an immutable image. We use them as workers. They host these micro VMs for our customers. And then we terminate them. We give them back to EC2, and they get completely re-imaged. And that allows us to make sure that we have a very small and well understood set of software deployments in our fleet, which is great for security and great for operational sanity. And then lesson three, this is the big thing from running the cloud, is the job is never done. Our customers are always asking us for new things, which is fantastic. They always have new needs. There's new hardware, the new new requirements, and there are always improvements to be made. And that means that something like Firecracker is always going to be under active development. We're improving it. We're putting in investment there. We're working with the open source community. It's there on GitHub. And you'll see us, adding new features, adding better performance, and so on over time. And that job is essentially never going to be done because the cloud is never really done. And then a quick note at the end on what we see as the future of micro virtual or micro VMs. I/O performance and scalability continues to be a challenge. The approach of having a software VMM means that we are currently, implementing VirtIO in software, and we have a lot of room to improve that software and are planning to, but that's always going to be something of a challenge. And so what we need is the I/O performance and scalability offered by offload, like we do in EC2 with the Nitro system, but at the same density that we need to run serverless. Scheduling, especially at these high densities, is a challenge around tail latency, especially as you try and drive up CPU utilization. And I think there's some real research opportunities there and industrial development opportunities. We're working with the formal methods community to to prove some more of the security properties of Firecracker, and be able to have even more confidence in the security of some of the paths through that code. And there's some really interesting work that can go into research into formal methods. There are a bunch of features that we would like to see implemented in Firecracker, some of which we're working on ourselves already, like snapshots and ballooning. But also lots of opportunities for building more features into this micro VM. And one thing I'm really excited about this space is the REST VMM project. What we've done with REST VMM in partnership with folks like Intel is take some of the core pieces of Firecracker, break those out into a set of libraries for building VMMs in the Rust programming language. And we've already seen folks build stuff like Cloud HV on top of that REST VMM core. And REST VMM is this essentially growing library or toolkit for building VMMs in Rust, and it's all open source, it's all available, and I think it's the beginning of something that is a really great trend towards mission specific micro VMs and isolation. And we're also excited to continue working with the container community to raise the bar for container security for everybody everywhere. Thank you. I've been Mark Brooker. I will be happy to answer your questions.